Swayam Prabha. Digital India. Educated India.
Welcome. So we have been discussing long-term plasticity implementation in computational models using different kinds of rules of update of synaptic weights, or actually we have been talking about how the change in synaptic weights take place with using the derivative of uh, the elements of the weight matrix with respect to time, and that is some function of the input activity u, which is multiple number of inputs, and the single output variable v. And so we have these rules that we have considered are the correlation based rule, the covariance based rule, and the BCM learning rule. And so we saw that the BCM learning rule overcomes most of the, rather all the problems that are associated with the Hebbian based correlation based learning rule or covariance based learning rule, and appears to work very well. However, there is one issue that comes in, is that the weight updates stability, that is the stability of the weight from, or the length of the weights not growing unbounded, that is indirectly controlled through the output activity. So in other forms there are normalization models, normalization based rules, that actually constrain the weights directly. And so we have two kinds of normalization based models. One is the subtractive normalization, and the other is multiplicative, or in fact it is actually divisive, multiplicative or divisive normalization. And this is also called Oja's rule. However, we must also say that these rules that we will talk about, the subtractive and multiplicative rules, they are not totally biologically grounded. As we will see, the subtractive rule somehow requires information from all the synapses to each of the synapse, which is may be plausible, but there is no evidence in support of that. And similarly, the multiplicative normalization is more a mathematical way to normalize it, rather than how actual sort of normalization works in terms of homeostatic plasticity, where the overall weight is overall response activity or output activity is over long periods of time, is that average is maintained. However, so since these are used in a number of computational models that include plasticity, and these are some of the basic rules, we will be covering them in this course, in particularly in this lecture. So what do we mean by the subtractive learning rule? Essentially, we introduce this idea that the sum of our weights, that is W1 plus W2 up to our WNB, where there are WNB weights, this is constrained to be constant. So, in other words, if we define a vector n that is all elements are unity, then n dot w is what this sum is the dot product of n and w. So, our learning rule, that is our tau w dw dt, is given by our v u, as we always have, and that restriction is brought in by v n u times n divided, or n vector n times n b. So, this is the correlation based increasing part, that is the weights would be increasing. So, that is countered by this particular term, which is based on again both the output activity and the input activity, and it is made to be of this particular form, so that ultimately our sum of w, this n w does not change. So, for the n dot w, for not changing, the derivative of n dot w must be 0, and so let us see what we have. So, d n dot w, which is the this is the sum of all the weights. This will, we require this to be constant, and that is why that additional term has been introduced, and so this is nothing but the n vector dot dw dt, and our dw dt from our previous expression, we have dw dt equals we have v u minus v times n dot u times n divided by n b. So, now we simply plug this in into this term here, dw dt, and so we have n and a dot product with v u minus v n dot u and n divided by n b. So, now if we take the n in here, what we will get is v times n dot u in the first term. So, this becomes v n dot u, because v is a scalar, we can take it out, and n is multiplied by u, and we also have the same v n dot u here, and we can plug in the n inside times n dot n divided by n b. And so, if we take v n dot u as a factor out, what we get is 1 minus n dot n divided by n b. So, what is our d n dot w? That is the sum of the weights coming out to be. Here, as you see, if we multiply n with n dot n, we are essentially having 1 1 1, this vector multiplied by 1 1 1, this vector. So, it is basically sum of n b 1s. So, because this number of elements is NB, and here also the number of elements is NB. So, this becomes 1. So, sorry, this becomes NB. So, what we have is, if this becomes NB, then this whole term goes to 0. And so, what we have is our N dot W is a constant. So, there cannot be any unbounded growth here, and we still have competition among the synapses, that is, when one keeps on increasing or few of them keep on increasing, the others are bound to reduce and go down to keep the overall sum of weights constant. And while this is, when thinking of just the mathematical treatment, this is a very suitable kind of rule. There is hardly much evidence to justify this clearly, although this rule can be used to explain certain phenomena in networks, but this again brings up the issue of the biological relevance and how we want to implement certain things. Sure, if the objective is to solve a particular problem, and if this rule helps us to solve that problem, that is fine. But if the objective is rather to understand and build on the rules that are biologically based and see how they are different, then such a rule actually wouldn't be that much useful, because while we do understand the correlation based increase in weights, which is sort of the Hebbian rule, and we have discussed the biological relevance of that as well. This subtraction, this normalization, subtractive normalization is not entirely physically true, because as you see, the for weights to decrease or increase, the information about all the other weights on the neuron is required at a particular synapse. So, that becomes a difficult proposition. While it may be possible through intracellular signaling in some particular way or through even activity in some particular way, but so far there is not much evidence in favor of this rule being true in a real neuron. So, in the next rule, what we will be studying is, as we have said, the multiplicative learning rule or the multiplicative normalization. In this case, again, so there we had a subtractive a term that is subtracted. Here also we will have a term that is subtracted, but it will be proportional to the weight itself. And so, what is this is the Oja's rule. What we again have is tau w dw dt, and this is again we have our term Vu, and then we have our alpha V square and this term multiplication by W. So, since we the update is proportional to this weight W, this is what we call for this is what we mean by the multiplicative normalization, the normalization that is brought in by a factor of the weight itself. So, why is this I mean, what does it achieve in terms of the normalization? So, here if we look at the norm of the weight, so again if we look at our norm, the length of the vector, and we look at the derivative of it, then and multiply it by tau w, then what we have again is tau w times 2w and v u minus alpha v square w. So, sorry, the tau w can be dropped because this is our tau w into dw dt. So, then what we have here is twice our v into w dot u minus alpha v square into w dot w, which is simply the norm of w. So, what is our w dot u? W dot u again is our v, as we have always had. So, we have 2 times v square minus alpha v square norm of w square. So, we have twice v square times 1 minus alpha w square, or actually we can say twice v square by alpha alpha 1 minus alpha minus w norm squared. So, what we have the derivative of the norm of the weight, that is the Euclidean, here in this case Euclidean length of the weight vector, that is the dynamics of it, that is the derivative of it in steady state, that is when there will be no change finally, it will always relax to 1 by alpha, because ultimately when the system stops, that is when we reach no change in weights, the norm of dw dt being 0, our w norm will approach 1 over alpha. And so, essentially that introduces a constraint on the length of the vector. And so, here also we see that there is no unconstrained growth of the weights, because ultimately the w reaches a fixed value. So, both these normalization rules are useful for many computational models. However, in terms of real neurons, they have many elements that are not really supported by evidence so far. So, for us the main rule turns out to be essentially the STDP based learning rule, and that we will say will be representing by, in this case, tau w then dw dt. And so, remember, if we have a learning window that is based on let us say this particular learning rule that we have, let us say this versus this, let us say this is any function h of tau on this axis. So, this is the pre minus post or the timing difference. So, if we assume that over time all of the spike timing is actually getting implemented, all the spike time differences are actually getting implemented, and there is a continuous spiking going on in terms of the probability of spiking occurring, and so sort of the ensemble average, then this dw dt can be represented by a sum of 0 to infinity h tau times v t and u t minus tau. This term we have d tau and plus h of minus tau v of t minus tau u t. So, essentially here this particular term is all the LTP that is occurring, and this is the contribution of LTD. So, here you see that our previous V is correlated with the current U and weighted by the H in the backward direction in the negative axis, because we are integrating over 0 to infinity, and here we are correlating Vt and ut minus tau, where that is the past u is being correlated with the current output, which is to and is weighted by this h tau. Depending on tau, this correlation will be changing, and this particular term is for the right hand side of the learning rule. So, here it is the change in weight that we had discussed. So, the LTP and LTD are both included, and the difference from what we had seen earlier in terms of the experimental observation of spike timing dependent plasticity, we have changed it in the sense that we are now basing it on average rate responses, assuming that there is a probability of spiking associated with that output rate. And so, we can indeed set up this model to explain the change in weight based on the spike timing dependent plasticity. And now, with variety of h taus or even various depending on how the different systems, different neurons and synapses work, we can modify the U's in a manner that is based on observation, or even the V's that is based on observation, like we were talking about bursting activity and so on. We can have a general sort of model for change or update of weights. So, with these discussions of synaptic weight update implementations, we come to the conclusion of the modeling of long term plasticity, and next we will be talking about how these are implemented in networks, what are the consequences of both short term and long term plasticity in our coming lectures. Thank you.